So here we have a function in factored form. All right, the zeros of this function are whatever makes these factors equal 0. And so we'll get a -2 for that one. That's a 0. And we have a +2 from this one, and then a +5 from that one. So here's my +2, 3, 4, 5, and there's my +5. So here are the x-intercepts. If I wanted to graph this polynomial function, that's what I would do if I was in algebra. Algebra 1. No, I'm sorry, Algebra 2 does this. Okay, so my Algebra 2 students learned to do this at the beginning of this semester. The next thing you would look at is at the very beginning, there's no negative number, like there's just a +1 right here. And then you would, so because there's a +1, you would also look at the degree of this, and because there's 1, 2, 3 x's multiplying to each other, if I were to multiply this all the way out, my degree would be a 3. Because the degree is 3, I know that my endpoints would be, or my end behavior would be at the bottom left and then the bottom, or the top right. You guys remember this stuff at all? I don't know. So here's my function. It goes like, it'll go through that, and then it goes through that, and then it goes through that. Okay, now I didn't do another thing, which is actually one of the easiest things to do, and that's plug in 0 to my x's to find the y-intercept. You almost never not find the y-intercept because it's so flippin' easy. Just plug 0 into the x's, and that's your y-intercept. Actually, let's check this one out right here. Plug 0 to the x's, what do you get for your y-intercept? So if you did plug in 0, you got +20 because you go 2 times -2 times -5. So you get +20, so my y-intercept would be +20. Okay, you guys remember graphing this stuff? Yeah. Okay, now you know calculus. You can do a little bit more with these functions. You'll get dirtier polynomials. They have nasty x-intercepts. Okay, now how can we use calculus to graph these? Like let's pretend that we didn't know, we don't know what the graph of this is. Let's pretend for a minute. Okay, if you multiply out that function, so it's not in factored form, but it's in polynomial form, it'll look like this. It'll be f of x, and I wrote up on the board already. Let's put it on the screen. We have x to the third minus 5x squared minus 4x plus 20. And I have a question for you. Let me find it really fast. The question is this: how would you know where a function is increasing or decreasing without looking at a graph or the graph? How would you know where it's increasing and decreasing? Now, you calculus students should have an answer for me since you're only studying 2 things this whole year. You're studying the rate of change, which is also known as slope. So you're studying slopes. And the other thing you're studying is area, which is when we start doing integrals. And we haven't done that yet. So how would you use your study of slopes to find out where our function, this guy right here, is increasing, point at him, okay, is increasing or decreasing? Is there something about the derivative that you can use for this?
Yes.
Yeah. Mari?
What if you try finding critical points?
Ooh, critical points would be a fabulous question, or suggestion. Now, why would critical points be valuable to us if we want to find out where a function is increasing and decreasing? Yeah, now what you guys are thinking right now is monotonicity. Between critical points, the slope will always be one sign, right? It'll be positive or it'll be negative. When it hits another critical point, then it could change sign. Right? There's like, there's graphs that will do this. First, the graph is increasing, and then the graph is decreasing. First, the slopes are positive, then the slopes are negative. What is our critical point in this scenario? What is our critical point?
Directly in the middle.
It is known as
0.
a max.
A max.
Oh, yeah.
Right?
Yeah.
And then if it went like this, if the function went like this, it was decreasing and then increasing, your critical point would be called a minimum. Now, is there any other situation that could happen?
It's a horizontal line.
What if, well, a straight line wouldn't have a critical point. Now, would it? Because a critical point is where the slope equals 0.
An absolute value.
Could you have a critical point where the sign doesn't change?
What if it's a horizontal?
Looks like this.
Forever increase.
There's a critical point right there. The function is increasing and then increasing. Is that critical point a max or min?
No.
No. Now this looks obvious. I'm hoping it really looks. Does it look obvious? Okay. And what about this? Critical point right there. Decreasing, decreasing. Negative, negative. You guys see what I'm saying right here? Now this concept, monotonicity, relates to something very common in calculus, and they're called sign line graphs. And in sign line graphs, what you're doing is you're looking for where your function is increasing and where it is decreasing, and this is where the derivative comes into play. Now, critical points also come to you if you have an undefined slope. So don't forget, it's not only where the slopes equal 0, it's also where the points are undefined. So, how do we find our critical points? We've done this before. Tell your neighbor if you know. Right now, go tell him.
What does Olivia ever get to turn it?
That's how Wells Fargo has a carriage.
What you say has value.
You find out where f prime equals 0 and where f prime is undefined. Now, most of the time, the undefined one will only matter if you have like a rational function where x is on the denominator. That's most of the time. Okay, so let's get down to it. We're really going to focus in on this. This is most of the situations that you will encounter. First, we'll find f prime by taking the derivative of this. I wouldn't want to take the derivative of this because that's a lot of product rules to do. I would do this one. So we get 3x squared minus 10x minus 4. So we set this equal to 0. We have 3x squared minus 10x minus 4 equals 0. Now, I don't know about you, but I don't want to factor that, nor do I really want to use the quadratic formula. Can you? Yes, quadratic formula is actually a simple one to use for this, but I want to show you guys how to use your graphing calculator, so pull that out. I'm going to solve this using a graphing calculator. So I'm going to take this guy right here and throw him into my graphing calculator. There he is. So cute and pretty. And then I'm going to graph him just to look at it. And our answers right here and here are the x-intercepts of this graph. Remember, it's wherever this, our answer is going to be wherever this equals 0. So where this quadratic function equals 0. So, so what we got to do after we graph it, we hit this button right here, the second button, and then we hit the calc button. After we hit the calc button, we can hit the 0, number 2. The 0, remember 0 is the same word for roots, x-intercepts, or solutions. So I'm going to hit 2. And then it brings me back to my graphing window and it says, okay, where do you want to find, the calculator wants to know where do you want to look for an x-intercept, where do you want to look for a 0. So let's start with this 0 right here. I want to find out what that 0 is, and so it says, the calculator says, what is the left bound that you want to go to? Like, what is the number to the left of the x-intercept that you're looking for? And right here we can see it's going to be negative. Once I plug in -1, I hit enter. And it gives me this little asymptote looking thing for the left bound. Now it wants to know, what do you want for your right bound? And it looks like to the right of this 0 is 0. And I press enter. You can really pick any upper and lower bound, but you want to make sure you don't include two different x-intercepts, because then the calculator won't know what to do, which answer you want. So I could have picked -2 and +2 because there's only one x-intercept between those. But anyways, that's how you pick upper and lower bounds. Then the calculator says, okay, you want me to guess? And you say yes by hitting enter, and then it's going to give you a guess as to what the 0 is. So this 0 is x equals -0.36, and let's just round it to the nearest hundredth. So we can write x equals -0.36. Now there is another 0, so let's find that really quick. So I'm going to hit second and then calc again, and I'm looking for zeros, but this time I'm going to pick, see, 1, 2, 3, let's pick 3 and 4. So 3 is going to be my left bound, and then 4 is going to be my right bound, and then I say guess. Looks like the answer is 3.69, so I put 3.69 right here. Alright, so now I have my two x-intercepts for f prime. So this is where my critical points are for this function right here. So let's draw an x-axis. I'm only going to draw an x-axis right here. That's an x-axis. And I'm going to put my two critical points on this. I have negative 0.36 and 3.69. The question is this graph, these critical points, these x values, are where my function has a slope of 0. So this actually makes a lot of sense. Negative 0.36 is right about here. So it looks like my line is slightly off because it looks like I have a slope of 0 in the positive x zone, but it should be over here to negative 0.36. The other x value that has a slope of 0 is 3.69, so that would be right about here, and it looks like I did a good job of drawing that function. Now, what we want to do here is we want to find out where the function is increasing or decreasing. So in order to know if the function is increasing or decreasing in this section, and this section, we have to pick tester points. We have to pick a random x value in this section, a random x value in this section, and a random x value in this section, and find out if the slope there is positive or negative. Now you only have to pick one x value in each section and test them in the f prime function to see if the slope in this section is either going to be positive or negative. So let's test one of them. So in this section, since our x critical point is at negative 0.36, I can pick a negative 1. So I'm going to make this random x be negative 1. And so when I take negative 1, I'm going to plug it into my f prime. And we're going to see if it's positive or negative. You could probably do this in your head, but I'm going to write it out just for learning purposes. So negative 1 squared, and I have negative 10 times negative 1, and negative 4. This is going to be positive 1, so we have positive 3 plus 10, and then minus 4. Yeah, that's definitely going to be positive. So that means in this section right here, we have increasing function, which is true. See, we can see it right here. The function is increasing. But remember, we're doing this as if we weren't able to see the graph. Then we would pick a point between our two critical values. And we can pick 0, since 0 is in between these. And let's just plug 0 in our head. That would go away because we plug 0 into that. Anything times 0 is 0. That would go away. We would be left with negative 4. So that means in this section, we have a negative slope. A decreasing function which has a negative slope. And then the last one, we would have to plug in a number that is above the 3.69. So I'm going to save us some time and just say that it's positive because we know what that function looks like at that point, but we could pick like a 4 or a 5 or a 10, anything to plug into this to see if it's going to be positive or negative. And so that's it. That's what monotonicity is and how it's related to a sine line graph. This is your sine line graph. It tells you where a function is increasing or decreasing.